Oh, good evening, everyone. Welcome to the week 2 live interaction session. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. So, let's start our session. I hope my presentation is visible and I'm audible. Okay, so let's begin. I welcome you all to the week 2 live interaction session for the course Polymer Concept, Properties, Uses and Sustainability. This course is offered by Professor Abhijit Deshpande from the Department of Chemical Engineering, IIT Madras, under the NPTEL program. Myself, Pratyumnan, a teaching assistant and a PMR scholar at the Department of Chemical Engineering, IIT Guwahati. I conduct live interaction sessions for this course for this particular semester of July to November 2025. So, previously in the last lecture, we discussed more on the introductory concepts of polymers, where we had a brief, detailed discussion on what is polymers and what are the basic properties and very fundamental overlook on what is polymers, their uses, application, and a little bit we touched on towards the sustainability as well. So for week 2, if you see in our lecture or the course content, it is broadly, you can classify them into two different subtopics as polymer sustainability, and another one is the polymer conformations. So as we have already discussed even in the last lecture or last live interaction session as well as in the lectures, what we saw was that polymers have actually started blending with their life, blending with our lives. They are there in, they are there with us and we use them every day, and they you cannot come will they have blended with us so much that we can try to minimize the usage of polymers or plastics, but we cannot eliminate them. So when we are facing this kind of challenge, one of the ways to make or basically reduce the wastage of polymers, so the major concerning um, things about a major concerning problem related to this plastic or polymer is the wastage. How to reduce the wastage of the polymers after its use is over or after its service life is finished. So in order to do that, we need to think about how to make these polymers more sustainable. So that's where we come about the concept of polymer sustainability. Well, this is a very common thing which everybody knows, but then there is also another one issue with respect to polymer sustainability, which is obtaining of the monomers or basically the precursors of these polymers actually come from the non-renewable resources such as fossil fuels like petroleum and diesel. So last class we had a quite a short uh, understanding of how these polymer monomers, I mean the monomers, are basically derived from the petroleum products through cracking. And so these crude oils that you get from the underground is usually processed through cracking, which basically generates the small monomer or the small hydrocarbons which act as a monomer, which can be therefore polymerized to obtain the polymers. So this is another one aspect which makes the polymer, which makes us concerned when we think from the sustainability perspective of the polymer. So these are the two issues when we deal with polymer sustainability. So one thing is that the polymer raw materials, which is usually comes from the non-renewable resources. So how to basically go about getting these monomers, or how to make this process more sustainable and how to reduce the wastage of the polymers. So that's what was typically discussed in the first two lectures of this course dedicated for week 2. So what are the different ways in which we can start making these polymers more sustainable? So I hope by now you guys would have had some ideas on how to make them sustainable. So can you please tell me how to make this process entirely sustainable, or what are the key ideas which can be thought when we talk about polymer when we talk about making polymers more sustainable. Using the Okay, so one way is to basically make sure that you try to make new kind of like go for a completely different monomer. So since as we now discussed about the fact of deriving these monomers from the hydrocarbons, we can actually think about making these monomers from some other material or which is renewable in nature. That is one aspect. Then another one is to basically make sure that we come up with the polymerization technique or normal polymerization technique in such a way that we can have a polymer which is which is biodegradable, so that the wastage does not remain as does not remain in the ground, but also have the similar properties compared to their synthetic counterparts. So It's something like saying about having making Teflon or making a polymer very having similar property to that of the Teflon, but at the same time it should be biodegradable in nature so that we can reduce the wastage problem. Apart from that, so one is monomer, then another one is the polymerization route. Apart from that, so modifying their properties basically so that we can have something very similar to the polymers that we current the synthetic polymers that we currently use. So like this there are techniques, and what when we think from the perspective of making the polymers renewable or make or from the sustainability aspect, we discussed about um, two things. One thing is the in vitro polymerization and another one is the in vivo polymerization. So in case of the in vivo polymerization, it is also called as the bacterial polymerization. So wherein the bacteria actually produces the polymer within the cell, or basically the polymer gets produced within the cell, and then these polymers that are produced are ejected out from the cell as excreta. So through these ways we can make the polymers more sustainable. And one more interesting fact that has, I'm not sure how many of you are aware of this fact, is that they have found out the researchers have found out that there is a fungi which is basically in the forest, in the Amazon forest if I'm not wrong, which basically feeds on plastics. So they feed on plastics and then they degrade those plastics into smaller components. I hope you guys are aware of that. So you may look at in the internet. So this is a very recent, somewhere few months back in 2025 only, we had this news coming up from them that they have found out a fungi which basically feeds on the plastics and then breaks them into smaller components. Smaller components, in the sense digest them. So the major aim to generally talk about the polymer sustainability is to basically make sure that we are able to generate engineering polymers or engineered polymers through these techniques, so that they have their properties superior to that of the synthetic counterparts, as I just said. So once these polymers are made, so whatever we were talking about the waste, we should also basically think about the biodegradability aspect of the polymers. So for that we think about the concept of depolymerization, where the polymer chains are broken down to form smaller components using enzymes, which are then taken up by the environment. So in the last class, I hope you guys remember, we discussed about a question. uh, Question number 4. The question was, which of the following is an example of a biodegradable polymer? And we had four options. It was a GATE 2023 question. So the four option was polyethylene, polyamide 6,6, polypropylene and polylactic acid. And I specifically, I remember that I asked the question of why polylactic acid is a biodegradable polymer. So I hope with the week two's contents discussion, you guys will be able to say why polylactic acid is biodegradable in nature. Why not others? So two reasons. One thing is, as you guys last class, you people told that it comes from, it is a natural source. Then the second thing is what someone just told right now. So the polylactic acid, basically, if you see, this has a C double bond O, I mean ester linkages. So these esters are susceptible to attack by some sort of an enzyme or the bacteria that is present in the environment, like lipases or something, so some sort of an enzyme. So because of this reason, these polymers are come under the class of biodegradable polymers, because they are more susceptible towards attack from the enzymes and the bacteria present in the environment, and because they are susceptible to attack and break down upon the action of the enzyme and bacteria. So that they can be, so that they are broken down into smaller molecules which can be then taken up by the environment, and that is the reason why polylactic acid is one of the biodegradable polymers. So this is about the concept of polymer sustainability. After polymer sustainability, we have few discussions related to the states of interest, wherein we discuss about crystalline polymers, amorphous polymers, and then we move on towards their application. Then later, so these are some of the things which we will not be discussing in this live interaction. So we now move towards something called polymer conformations. So more related to what is what we call it as polymer physics, what comes under polymer physics. So conformation as such, I hope now you guys might have understood the meaning of this term. So conformation is nothing but it's basically about the what do you say, position, or basically the arrangement of the molecules, arrangement of the atoms, or how atoms are typically arranged within a molecule. So that is what is basically called as the conformations. So if you see, the most in any case, the most preferred conformation state or most preferred state for any molecule will be the energetically least state, or where the energy of that particular molecule is minimum. So in excited state, which, what I mean is the higher energy state, the molecule will not be stable at all. So it's something very similar to humans also. So majority of us want to be always in a relaxed state where our energy is getting less consumed. So people used to be in excited state, but then that is only a short-lived state. So moving on towards here, these polymer conformations are something which is, as I said, it depends upon the position, or basically that of the arrangement of the atoms, or how atoms are arranged within the molecules. So in case of crystalline polymers, what we see is that these conformations are not possible. They are only crystalline polymers have only bond vibrations, whereas conformations is not possible in case of crystalline materials as such. So any idea on why so? So what we discussed was this conformation is something that is that is very common only in case of the polymer melts and rubbery polymers. So I mean, when the polymers are in the rubbery state. What about the crystalline ones and the amorphous ones? Why do you think there the conformations are not possible? Any idea on that? Because probably they are fixed under corrosion. Hmm. So that's exactly what correct. So what happens is, in case of crystalline solids or crystalline polymers, they are basically bonded together. Their bonds are typically very rigid, and then the atoms are very immobile. So since the atoms are very immobile and they're tightly bonded to each other, the rotation is not possible. Bond rotation is not feasible there, and due to that the conformations are not possible in case of crystalline materials. And in case of amorphous, apart from bond vibrations, they only have this what do you say, the side groups rotation. So apart from that, it is much of the conformations is not possible in this case. Whereas in case of the rubbery state of polymers, or basically in case of polymer melts, since in order to make these rubbery state or basically the polymer melts, you need to increase the temperature. So as the temperature is increased, these bonds becomes more mobile because of the enhanced kinetic energy that is imparted to these atoms, and due to which they start to exhibit some sort of a rotation, and therefore these conformations are possible in case of this polymer melts, or basically in case of the polymer melts. So these conformations basically give a lot of understanding about the properties of the polymers and how the polymer properties vary across the different states of matter. So in case of the polymer melts, the properties of the polymer will be very different because of the changes in that occurs within the uh, conformational states, you can say. So talking more about this confirmation, we actually move on to discuss more about the um, discuss more about how these polymer conformations are modeled. So we first discuss something about this coarse grain model. So I hope I mean people here may have a understanding of that. So okay, let's see. So chorus grain model is nothing but over there each of the the repeating units are there, right? So that is basically assumed as uh, a grain. So that's how the name comes. It's just that yes. No, you just ask, then it will be better. No. It's just that the polymers are for having that confirmation, and in order to model that, we basically consider them as uh, you know a grain. So that is the thing. It's not like because of them we are considering this, they are exhibiting the confirmation. So it's just that to make things a bit simpler for us, so we basically assume these kind of I mean the scientists have come up with this kind of model. That's the reason it's called coarse grain model, because they actually, in order to, I mean, these polymer conformations are quite complex in nature, right? So, in order to basically give mathematical model or mathematical sense to them, they basically model these polymers as coarse grain, and then they define these, what do you say, the many things like end-to-end vector distance, contour length, radius of gyrations. I hope we will be discussing that as we progress through that. So, what is the most, as I can say, favorable state for a polymer, or how does a polymer? What do you can say that you can say favorable state for a polymer? How the polymers will be something like a coil shape. So there will be multiple. What do you say? So they will be in a coiled shape where multiple macromolecule chains will be there. So here we basically describe about few kind of technical terms, so that I'll be writing it here. The first one is the end to end vector distance. So here what we consider is that we consider every single bond as a vector, and the distance between the first vector as well as the last vector is what we call it as a end-to-end vector distance. So second one is basically the contour length. So what is this contour length? The actual length of the polymer, of the macromolecule, you can say. The reason why what is the case is, if you see in a polymer coil, the end to end vector distance will be less than the contour length. So can you just tell me a situation, or basically a configuration when this end to end vector distance and the contour length will be same? Basically, you can say when it is in a stretched state as in, so end to end vector distance will be equal to contour length when the polymer is stretched. So initially we basically you describe most of these polymer conformation. We assume that these polymer chains are ideal chains, and why it is ideal chain? I mean, why it is called? Why we basically say this polymers as ideal chain, or how we say them? Or what is that consideration that we keep when we say these no interactions between the polymer chains here? So this is basic. So this is the basic assumption that the molecular interactions between the different parts of the chain are not present, or there are no interactions specifically. So in so we basically describe this. So based on this end-to-end vector distance, and then this contour length and the molar mass, we basically come up with the relation wherein we say that the end-to-end vector distance and then the molar mass exhibit a Gaussian distribution. So because these chains are in case of this ideal chain model, the polymers basically typically exhibit this Gaussian distribution. Then we basically move on to the concept of radius of gyration. So RG. So distance between the, yes, radius of gyration. Distribution, center of mass is fine. No, where we are taking that point. This is fine. It's basically the distance between the center of mass and a point where, like, uh, excuse me, Yasmin, are you there in this meeting? Yeah, can you just unmute? Yeah, sorry, mute yourself. Yeah, distance between the center of my mass and any point. I mean, it should be there in that chain, right? That point. Yeah, because I mean, you basically take that entire chain. There are so you basically find the center of mass. From that center of mass, whichever point you basically measure on that chain, that distance is what you call as radius of gyration, RG. And this RG is given as R naught square, oh sorry, by 6. So if you are interested, you can always sorry, this is RG square, and this is a relationship, and this RG square is typically defined as 1 by ns, uh, minus r of c. Rc is basically the center of mass, and Ri is basically the point which you are basically taking under consideration. And this particular relation Rg square equals to R naught square by 6 is actually it comes from a derivation, so you can always look at it, but it's quite complex, so that's the reason we take this as a relationship here, and then we basically progress towards solving some of the questions. So in case of the polymer chains, so what we basically describe is that these macromolecules, what you take, they are basically after this, what we describe is that the macromolecule is, so when you apply shear on these macromolecules, they tend to get stretched. So as we know that in case of a relaxed state or in normal condition, the polymer usually used to be in a coil shape, but when you apply a shear, it basically gets stretched. And when you remove this, what happens is there is an elastic recovery of these macromolecules, and then they tend to return back to its original shape like a spring. So that is the reason why we basically model these macromolecules as a spring, and then basically apply the uh, we basically model these macromolecules as a spring, and then basically correlate this to a Hookean spring, and then we derive few relationships. Some of macromolecules. So here that the macromolecules are considered to be a spring, which returns back to its original shape after the after removing the deformation. Since this exhibit a spring type behavior, we kind of, what you can say, we compare this with the Hookean spring and derive the equations. So you have this force equation. I hope you guys are able to remember, or otherwise I'll write it down here. So the force in that spring can be written as 3 times RT by, so I have written it like this here, but when you get this PPT, these will be represented in their proper notation form, because since here it is very difficult to write these, I have written it like this. So this is what is the main reason. So if you see here, this force is basically proportional to the temperature. So what we, so since this force is directly proportional to temperature, the spring force, the spring constant is also going to be directly proportional to the temperature. So what it means is, if you increase the temperature, the spring constant is going to increase, so the modulus of elasticity is going to increase. So that is the reason why basically rubber exhibits increased modulus with temperature. Because of this conformation changes, these rubbers exhibit increased modulus with temperature. And another one condition is basically the charge condition. So the you can say, when you have this polymer in the neutral state, it is basically in a coil shape, and when you add charges to it, what happens, when you add charges to it, the charge entirely gets delocalized over the entire chain. And because of this, what happens is, since there since everywhere there is a similar charge, different segments of this polymer will repel, and due to this they will go into a more extended state. So like that we have so depending upon this polymer as well as that of this solvent interactions, we have multiple different types of, we classify the solvent as theta solvent, then good solvent, then bad solvent. So theta solvent is basically a solvent where the polymer chain interactions are absent, so that is one of the most ideal cases. Then we have something good solvent where the polymers will remain in its most favorable state, and we have something so called as bad solvents, where what happens is this polymer interactions are so high that they interact with each other and form aggregates and clumps and settle down as precipitate. So that is typically a very bad what do you say, a solvent for this, for the type of polymer that we are choosing. So after this we have some discussions on polyelectrolytes. So what kind of polymers do you think can be used as polyelectrolytes, or what kind of polymers classify the definition of polyelectrolytes, or uh, yeah, you can say that way. Hmm. Yeah, that is the example. So, what is that basic thing that a polymer should have so that it can be called as a polyelectrolyte? Typically, it should have ionics groups in their system. Ionic groups which can dissociate in solvents. Typically speaking, mostly it should be a polar solvent. So this is basically the definition of the polyelectrolyte. So here actually, so basically these polyelectrolytes are used for, in many cases these are used for this water separation or kind of this desalination application. Then it is used as electrolytes for battery applications, wherein you can add salts to the polymer. I mean, not necessarily that all the polymers contain charge with them or contain these ionic groups, but still they are used as electrolytes. But they do not classify as polyelectrolytes, but they can be used as electrolytes. So these polyelectrolytes typically have, as I said, applications with the desalination, where you require anionic or cationic polymers for the separation of salts from water. Then it is used in some sort of battery applications and energy storage applications, and even in case of fuel cell application. So that common, the most commonly used membrane in case of the proton exchange membrane fuel cell is the Nafion. So any idea of what this Nafion is, like what is the chemical name of this Nafion? So it has a name. If you can actually go in the internet and then check. So Nafion is a commercial name which was given by a company called DuPont. DuPont. So the Nafion is nothing but it is, the chemical name is PFSA. So PFSA means perfluoro sulfonic acid, perfluorosulfonic acid. So what it what it is that it has a PTFE backbone, and then this SO3H groups are attached to this PTFE backbone as pendant chains or side groups, you can say, and PTFE as the backbone. So what is the main reason for using this is, so what happens in case of this proton exchange membrane fuel cell is that in the anode you have, so I'm going to just touch upon how this PFSA works in case of the fuel cell. So in case of the anode, what happens is you actually supply the anode with hydrogen gas. So this hydrogen gas is going to be, this hydrogen gas will give H plus ions plus 2 electrons. So this H2 gas is going to be oxidized to form H plus ions and then give out that electrons. These H plus ions that you gets generated at the anode side, what it does is it basically goes and then starts interacting with the SO3H group of the membrane. So over there what happens is this SO3H group actually is in the form of SO3 minus, sorry, and H plus. So this H plus that gets generated at the anode, it goes and then it interacts with this SO3 minus and H plus and knocks out this H plus ions from this SO3 minus what do you say, site, and then occupies that particular place. So this H plus ions that gets knocked out from this SO3H group goes and then interacts with the another SO3H group and then knocks out that ion from there. Like that it keeps happening until it reaches the other end of the membrane. So if you let me just put up a picture. So if you consider this as one side, uh, so if this is one side, and then if these H plus ions are going, and then it is going to attack this SO3H group, and as I said that this H plus ions will occupy the site of this H plus in SO3H group, and then the knocked out H plus ions will go and interact with another SO3H group, and this keeps on happening until this until that H plus until one H plus ion comes out on the other side of the membrane. So it does not get actually transported. It basically gets, what do you say, kind of it gets, you can say some sort of a hopping process takes place wherein this H plus gets interacts with the SO3H groups, knocks out that H plus, that H plus interacts with another SO3H group, and then this keeps on happening, and at the end one H plus ion comes out on the other side. So this is typically the mechanism of how this Nafion membrane works, and we call this diffusion mechanism, or you can say this kind of transportation mechanism as Grotthus structural. I hope I'm writing this correct. Diffusion mechanism. So here the H plus ions are not directly transported through the membrane. They basically go and kind of knocking out process happens, and that H plus ion that gets knocked out keeps on repeating, the process keeps on getting repeated, and at the end it knocks out another H plus ions which comes out on the other side, and of course then the cathode reactions will take place to give out water, and um, to give out water as a product, and this electron will be responsible for the energy generation. So this is basically the principle. I just wanted to just give a little bit discussion on how the PFSA works. um, so this is the place where our week 2 session ends, like I mean, the course content for week 2 ends. So we have around 10 questions to go, I mean to discuss today. So we can start that, but if you have anything that you want to discuss, because I polymer conformation is quite a difficult topic as such, because it basically involves many things which many of you may not, maybe hearing that for very first time. So yeah. Hmm. No, that R will be more the. Just a second. Wait a minute. Now, which R you are actually talking about here? I mean the R at the bottom. This one. Okay, okay, okay. Hmm. 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 Yeah, yeah, there's an ensemble average on that. I mean, I degrade. They do not easily degrade. So that can also be one of the examples. But do we have any yeah? Keratin. We have to check how what is the degradable. I mean the degradability span. How long it takes to degrade. So what will be the answer for this question? False. And in case of some examples, you can say chitin, and as someone said, lignin to an extent. Actually, these all depends upon, these all we are saying they are not necessarily biodegradable because the span of time that requires for their degradation is quite long. Now let's go on to question two. Question two will be a bit I wouldn't say tricky, but it would be quite you can give it a try once. Urea. Urea is NH2CO NH2, so that may not be a monomer. Yes, I mean one of the monomers has nitrogen in them. So you can. I'll just give one option because that may be one of the reason why the second monomer is difficult. So the one of the monomers is melanama, melamine. Any guesses on what I mean, or any guesses on how does this melamine polymer, I mean, sorry, melamine monomer looks? I mean, any idea on its structure? This is the GATE 2023 question. Yes. So then, what could be the other? I mean, I gave one. So what could be the other one? It has two monomers. One is melamine. So melamine, as somebody told, it is actually that if you see you will have that benzene ring, that sorry, if you will have that heterocyclic ring with three nitrogen atoms, and the other three positions will be connected to NH. So that is melamine. So what else we have to add to this to basically make this polymer that you see here in this figure in question 2? No, you need to say the. Okay, I'll give one more clue. It will be condensation polymerization. I know it without options this may be tricky, but you can always. I mean, the reason why I gave this question was, if not now, you can actually take this question and then you can try with few groups that you can. I mean, I've given two clues now. One is one monomer, and another one is what kind of polymerization it is has to go under. So you can try to, do some sort of a trial and error, and then you can get the second monomer which is used in this polymer. So this I will leave it to you guys. You can take this as it could be a fun task, because you need to think about many different kinds of monomers, and then you have to come up with the structure. But let's discuss this in the next session, because we last entire week we saw questions related to giving two monomers and then really asking what is a polymer that is going to get formed, or some sort of like what kind of polymerization reaction will be formed. But we never gave, or we basically discussed more on finding out monomers of common polymers like nylon 6, nylon 6,6, but we didn't see something that is something only where the structure is given without its common name, and then uh, we have to find out the monomers. So there are two now, what do you say, kind of clues. One is that one monomer and what kind of polymerization it can go under. So you guys can give it a try, and then we will take up this in the next class. So moving on to question 3. Which one of the following step is not a part of the sequence of step for depolymerization in biotic world? As I said, depolymerization what it typically means is breaking down of polymers into smaller monomers, or basically into smaller components, so that they can be further used up by the environment. C. Any other answers other than C? Any? So yes, this is a straightforward question. So only C is not a part of this part of the depolymerization process. And why is it so that C is not a part of this depolymerization process? Sim- but here it is written as it is helping in cross linking of the structure, which does not make sense. I mean, it goes against the definition of depolymerization. So the option is C, because apart from that, all the other options like attacking the backbone of the polymers, then the products are basically used up in microbial cell for carbon and energy source, and at the end conversion to carbon dioxide water. All are something what we expect or what we want from this depolymerization process. So it's only C which is sort of going against the definition of depolymerization. Question 4. Which of the following is not a correct statement of PHB? What is PHB? And any polyhydroxy butyrate. I hope the spelling is right. So, what is its? I mean, I should not. I mean, because it's not possible for you guys to draw. So, I'll just show the structure. So, since this is online, it is not possible to show the drawing. So, this is the polyhydroxy butyrate structure. So, you have a ester group and then a methyl group, and I think it is a. How many carbon atoms will be there in polyhydroxy butyrate? 4, right? Because butyrate and then, yeah, 4, 4. So this is the structure of polyhydroxy butyrate. So let us come to this question, which is not a correct statement. PHB is a biodegradable. PHB is produced and stored as energy source in the cell, similar to fat in animals. PHB is a polyamino acid. Property of PHB is very similar to propylene in many aspects. So somebody has told C as the answer. So what about others? Is this right or so if it is not a polyamino acid, then what kind of polymer is this PHB is? Some, it's a polyester group. And that is the reason why it is a biodegradable polymer, because these polyester groups, as we previously discussed, like PLA, they also have the same reason that these ester groups are susceptible to attack by the enzymes, as well as that by the enzymes present in the environment, and thus and thus these polymers are biodegradable in nature. So PHB is a polyester group. So let's move on to next question. Question 5. Phenol Phenol formaldehyde resin is prepared by condensation polymerization, cationic ionic ring open polymerization. Phenol formaldehyde resin is a very commonly used you can say resin in our daily life. It's commonly used. What kind of polymerization is does this phenol and formaldehyde go through? A. Okay, yes. Condensation, polymerization. So we need to actually, whenever we discuss these things, we also need to have idea, or like what I say, have to, mm, you can say, think critically. Like if I give, let's say, two different monomers to you, we should be in a position to know what kind of reaction can these two monomers undergo so that they can form the polymers. So if you see phenol and formaldehyde, phenol has OH group and formaldehyde is an aldehyde. So HCHO. So there are lots of possibilities that these two can interact with each other and undergo condensation polymerization to form phenol formaldehyde resin with the water as one of the byproducts. Because ring open polymerization is not possible in this case because there is no ring as such, and as such cationic and anionic polymerization is also is not possible in this case. So only option is condensation polymerization. Next question is something very similar to what we discussed previously. So lipase is a natural enzyme which cleaves carboxylic ester bonds. So as I said, PHB, uh, some sort of PLA, all have these ester bonds with them. They are typically polyesters, and then these kind of natural enzyme like lipase cleaves their carboxylic bonds. Among them, identify the polymers that can be degraded by lipase. Only PET. Yeah, D PET is correct. That is one of the that is the correct answer. Polycaprolactone. That is also, it is one of the it also has an ester bond which can be cleaved using this lipase enzyme. So let me just show the structure. I'll Yeah. So polypropylene, as such, everybody knows that methyl group in place of the hydrogen atom of the ethylene molecule, then you get propylene. Then you have polycaprolactone. So this is the structure of polycaprolactone. So here also you have an ester bond. So these ester bonds are also susceptible to attack by lipase enzyme. PET, polyethylene terephthalate, where it is nothing but it's a polymer of phthalic acid and ethylene glycol. Oh sorry, terephthalic acid and ethylene glycol. So that is polyethylene terephthalate, PET structures. And then you have PVDF, polyvinylidene difluoride. So you have two fluorine groups. So this is the structure of the PVDF. So this ends the concepts of, what do you say, the MCQ type questions. Now we will go towards solving some problems. I hope do you guys have any doubts only related to this six question? The other queries, whatever was raised, I'll come back to that by the end of this session. So anything here in these MCQ related questions? They are quite simple. So, but in case if you have, then you are welcome to ask. So, can I go towards solving problems? So, let's start first with question number 9. This is previously we have solved these questions. I hope now people might have much better understanding on weight average, number average, molecular weight. So, let's solve this question. It's a very direct question, but again, you need to be careful when you solve it. Specifically, when you are going to, you have to be careful when I tell these terms like total mass of the mixture. So, there you need to be a bit careful on. So I'll read out the question. A monodisperse polymer sample. So here so dispersivity is 1. Of molecular weight 10,000 gram per mole is mixed with another monodispersed sample of the same polymer of molecular weight 50,000 gram per mole. Total mass of the mixture. Again, I am stressing it is total mass is 1000 grams, and the total number of moles of the polymers, that is of both the polymers together, it is 0.04 mole. Now, based on this data, they are asking us to calculate the weight average molecular weight, number average molecular weight, and polydispersity index. So, obviously, if you get A and B, then C is just, it's I don't think it will take long. It is not a big deal. Any answers? So how to go about solving this? So let's take one of the sample like last time how we did sample P. Just a second once. Okay. So sample P molecular weight is 10,000 gram per mole, and sample Q has a molecular weight 50,000 gram per mole. Now it is written that the total number of moles, that is NP plus NQ, is 0.04 moles, and it is written total weight of the mixture, total mass of the mixture, W is 1000 grams. So I hope people will be now having an idea on how to calculate this, what what does this W represent. So how to write W in terms of N and M. Because once that logic is up, is you are able to get it, then everything is just mathematics, simple arithmetics. Ah, yes, okay. WT. So WT will be WP plus WQ. So what will be this WP and WQ, or how do you represent this WP and WQ in terms of this a number of moles of that polymer and the mass? NP plus NQ times M times MQ. Is this fine? Or is this correct, or anything is missing? Or so here we do not have let me put this sample P molecular weight as MP and MQ. So let's take one of the sample like last time how we did sample P. Just a second once. Okay. So sample P molecular weight is 10,000 gram per mole, and sample Q has a molecular weight 50,000 gram per mole. Now it is written that the total number of moles, that is Np plus Nq, is 0.04 moles, and it is written total weight of the mixture, total mass of the mixture, W is 1000 grams. So I hope people will be now having an idea on how to calculate this, what what does this W represent. So how to write W in terms of N and M. Because once that logic is up, is you are able to get it, then everything is just mathematics, simple arithmetics. Ah, yes, okay. WT. So WT will be WP plus WQ. So what will be this WP and WQ, or how do you represent this WP and WQ in terms of this a number of moles of that polymer and the mass? NP plus NQ times M times MQ. Is this fine? Or is this correct, or anything is missing? Or so here we do not have let me put this sample P molecular weight as MP and MQ. So NP plus NQ we do not have anything, I mean we do not have individual NPs and NQs, but we have MP and MQ and we have WT. So it just now arithmetics only, as I said. So I can write this as NP. I'm going to take it as 0.04 minus NQ, and if I do that, then WT will be nothing but, or yes, okay, first let me write it in that time. Point 0.04 minus NQ times MP plus NQ times MQ. So this is just pure mathematics. So it will be like 1000 equals to 0.04. I'm going to take that MP inside the bracket. So NQMP plus NQMQ NQMQ. So now you can take this 1000 as 0.04 MP plus NQ times MQ minus MP. So what will be that? So it was nothing but 0.04 times MP, that is 10,000, plus NQ, which we need to find out, times MQ minus MP. 50,000 minus 10,000, that is 40,000. So what will be the value of NQ? Anyone has calculated this value? So this will be something like 600 by 40,000. So 6 by 400. So that would be 1.5. 3 by 2. So is this the value of NQ? 0.015. Yes, I mean, has anybody calculated? It's better like to solve it parallelly so that it will be a practice. I guess I hope most of you would have seen your assignments. You can get similar, you might be having similar questions to solving like this. If not the entire, then probably one or two of them. So if this is the value of NQ, then NP will be nothing but 0.04 minus 0.015, which is 0.025. So NP and NQ you have it right now, and I hope you know the formulas for weight average. So anyone, the formula for weight average? So there is a specific reason why I am typing, because so that it looks, everybody can see that at least everybody take a pen, you guys can actually take pen and paper and solve, so that we are going step by step. So that is the reason I'm typing it here, because it would be more beneficial for everyone, me myself as well as you guys, so that you can see if there is any mistake is happening or how to proceed about that. Rather than, it is also possible that we can, if you guys are okay, then we can have like myself having a already solved answer and just explaining, but as far as I'm concerned, I prefer this method. So what is the weight average? NI mi by Ni, and oh sorry, and number average will be same thing, but it would be having just a square here. So number average is the first one. So I mean, everybody agree with that? So this is the number average, and this one is going to be the weight average. So what is the value? So you have your, I'm going to again write down the values here. NP is 0.025. NQ is 0.015. MP will be 10,000 and MQ is 50,000. Again, gram per mole, and these are just moles. So the value of number average and weight average. Yeah, what is the answer? So for weight average, it's just going to be NI square. So NP, I'll just write that. NPMP square plus NQMQ square by NPMP plus NQMQ. So now I hope you guys will be able to calculate, and the number average will be same. NPM NQMQ by NP plus NQ. Is there any doubt with these formulas of weight average and number average, like not able to understand, or is there any confusion in this which is basically preventing you guys to solve this problem? So since this is just more of a calculation, I hope you guys will be able to do. So what I'm going to do is I will leave this question to you. I mean, after this, the entire section, and then you can calculate this weight average, number average, and polydispersivity index, and I'll provide you the answers. So when I'm going to upload this presentation, I'll provide you the answers, and you can cross verify. And in case if you have any, I mean, if there is any calculation error, or if you find anything difficult, then you can ask me in the next class. So that would be best, I think, because, or if you guys have calculated, then you are welcome to say the answer to me now before we progress for another two more questions. Yes. Oh, somebody has 40,000, 25,000, and 1.6. uh what is your MW and MN like? Oh, okay, okay, okay. Oh, okay. So let, since one of them have given the answer, let me verify. Calculator. So it is NPMP 250. 0.015 times 50,000, 750. So that will be 1,000 by zero point zero 0.04. 25,000. Is this the answer? 25,000. Let's see. Yeah, Mn is 25,000 gram per mole. So this is correct. So I hope the weight average is also, the reported answer is 40,000. So, and polydispersivity index, as one of the attendees have said, it is going to be 1.6. So let's go to this question. Number average molecular weight of a polymer prepared from this monomer is 24,000 gram per mole. The conversion of the monomer required to reach the above molecular weight is dash percentage. You have to tell what percentage it is. This is something different compared to what we solved previously. So how do you proceed with solving this question? Just the idea. Yeah, yeah, sure, sure. Hmm. Yes. Hmm. Hmm. Okay. Hmm. Okay. Then that what you were saying, that number average molecular weight divided by this what do you say, molar mass of uh, the one unit is basically your degree of polymerization. But I am asking about conversion. So that is one step which is correct. But apart from that, there is some one more step. Mm. So can you just tell? Mm. So P is the extent of reaction, and if you calculate the P, then you will be able to calculate how much is that conversion of monomer, that percentage. So can you just tell me how much is the answer? I don't think it will take a lot of time to calculate this. Only the thing is, I think it's just straightforward. Only the thing you actually need to calculate is this, the molar mass of that molar mass of this one. So 140. So okay, let's before the answers, what is that value of that what do you say, that mn by mo, right? Molar mass of that, of this unit. So what is that molar mass value coming up to? Are you saying the percentage or the molar mass? Are you sure? Because it is a. I'll just read it aloud. So it's OH CH2 14 COOH 258. Okay. So molar mass of this unit is 258. Okay. But will we be taking this molar? The trick is here. The will we be taking this molar mass for calculating the degree of polymerization? 258 is fine. I'll just show, for in case if somebody is having different answer, I'll just show them. So 16 plus 1 um, plus 14 times CH2. CH2 will be 14. plus 12 plus 32, 258. So if according to as far as our this thing will be concerned, then it should be like the degree of polymerization should be 24,000 divided by 258, right? So that should be around 93.02. So, as somebody just told that 1 minus P, that is their extent of reaction, is 1 by this degree of polymerization. So, let me keep that as degree of DOP, or somebody keeps DP. Let me keep it as DP itself. So, that would be nothing but 1 by 93.02. So, 1 upon 93.02. 0.0107, and if you subtract, then P will be 1 minus 0.0107, which is 0.9893. So if you take it in the form of percentages, it should be like 98.93 percentage. But so is this right? In this entire process, there is an error actually. Anyone can guess what is that this thing? Okay, so I mean, uh, so then if that is the case, then what it should be? It's not very complex actually. Okay, what is the mm, how do you can just hmm. No, that's so let me just tell. So this is a monomer, and this is not the repeating unit. So when you calculate degree of polymerization, you actually divide that number average molecular weight to the molecular mass of the repeating unit, right? Because that's what is going to give you the polymer. So when you, so then this should be, it should be somewhere 240 if I'm not. So then you need to change the calculations accordingly. So I hope there is nothing much to discuss after this. That was the only thing that I wanted to tell. And regarding that question, somebody asked, right, what is the value of R in that FC by RT? So that should be this universal gas constant. So because this spring system that you are considering, this Hookean spring, actually the over there that stretching is based on this entropy of the chains, right? So when you talk about entropy, you need to basically express the force in terms of RT. So that R what you have at the numerator is going to be the universal gas constant. Like exactly speak, like what should I mean, what do you want me to? So let me do one thing. I will take the exact values. I will. It's better not to take random values because uh, whatever. I mean, it should not go against the science. So let me do one thing. What I can do is I can show a solved example. I mean, this PPT will be uploaded, so over there I can show you one of the examples while uploading. And um, and you can ask me if you have anything via email or through, or probably in the next session. Will it be okay? Because this thing, that's okay, right? Yeah, 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 okay. No, I will upload the presentation. So, oh, okay. So I hope you guys know that this session is recorded. I mean, are you aware of that? That this session is actually recorded. So this session is recorded, and it will be uploaded in YouTube. So what, how you can access this recording is that recording as well as the presentation, whatever we are doing it right now, is that in the course page, that is the wherever you can see, wherever you are accessing the lectures, if you see in the left hand side at the bottom, there will be a option of problem solving session. So if you click on that link, you will be directed to a page which again will direct you to another page where you can find a Google Excel sheet with that particular week's recording as well as the presentation. So you can access it there, and I will, so as one of you guys have requested for solving of one kind of problem of that type, I will solve that and then I'll upload it there. Okay, so so I think the deadline for assignment submission is on 6th, I believe. So I hope there will not be much issue with that assignment submission. And if you do not have any more things to discuss, then I think we can close the session for this week. Hmm. Oh, okay. So monomer be like that. So block copolymer is one. You will have one polymer attached to another polymer, like that. It will be in terms of blocks. One homopolymer will be attached to another set of homopolymer. and that in turn will be attached to some other some will be attached to this, let's say homopolymer A and homopolymer B. So first you will have homopolymer A, then homopolymer B, then again this homopolymer A will be connected, again homopolymer B, like that. So that is what you call it as block copolymers. So they will be in terms of, like, what do you say, together a set of them will be connected together, and then the next set it will be like that. You can actually Google and check. Yes. Yes. I mean today's session or okay. Yeah, here. So which question? Do you mean this one or hello? Ah, yeah. I mean, oh, okay, okay. Sorry, sorry. I didn't share the screen, so I have to share. Do you mean this one? This one? Uh, Answer. So you just take and divide this value and then proceed. So you should be getting somewhere around 99 percentage. Oh. Anything else? Okay, okay. And I guess one more person had something to discuss before we should. I think Nandini Shukla, do you have any more queries to discuss? P is basic. No, 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 no. P is the extent of reaction. How much is your monomer going to get converted? So, uh, P is actually the number of functional groups that are reacted to the number of functional groups that are available for the reaction. Okay. So let me close the session. So thank you everyone for joining. Our next week 3 live interaction session will be on 10th August. So both the video recordings as well as the PPT lecture will be available to you very soon by Tuesday or Wednesday, or maybe before that. So I hope you guys find this session useful, and I thank Professor Abhijit Deshpande as well as the NPTEL team for providing me this opportunity to interact with you all this Sunday afternoon, Sunday evening. So thank you, and have a great weekend.